Okay, so today we're going to finish up our lectures on welding. We're going to talk about dynamic loading of welds and also an interesting concept of thinking welds as a line rather than as a cross-sectional area. And this makes it really easy for us to be given a factor of safety and different materials and figure out what size of weld we actually need to make to build our machine. So let's go ahead and dive into the material for today. First, we want to start off by looking at the dynamic stress equations. We know that through a lot of testing that's been done, that when materials are loaded dynamically, they fail at lower stresses than when they're loaded statically. And there are a few equations that drive how we describe the amount of dynamic stress on a piece of material. First of all, we have the stress range, which is delta sigma, and that's just the maximum stress on the part minus the minimum stress. Hopefully you remember all these from when we've gone over fatigue previously. Should be pretty familiar. You've got your alternating stress, which is that sigma max minus sigma min over 2. You've got your mean stress, which is just the average of the max and min. We've got the stress ratio, which is the ratio of minimum to maximum stress. And we also have the amplitude ratio, which is the ratio of the alternating and the mean stresses. Now, an interesting thing about welds is that when they're dynamically loaded, through a lot of testing, it's been shown that the mean stress really doesn't have an effect on the fatigue strength of the weld. It's pretty much primarily all on the alternating and the range, particularly this stress range. This is the driver for how welds fail when they're loaded dynamically. So what you're seeing here is a comparison of unwelded material and welded material. So these guys are your welded marks, and then the others that are not filled are just a piece of wrought material. So what's really interesting to note is that you can see that the parts that have R of 1/4 and 0 and 1/2 and a 0 for the welded both have mean stress in those parts, whereas the last one does not. And one thing that's interesting is you'll notice, especially up here where these squares are, there's a distinct difference between when there's mean stress and when there's not. And when there's mean stress, the unwelded material fails at a significantly lower stress range than when there is no mean stress. But if we look at the welded material, that difference isn't nearly as clear. So all this goes to show is that mean stress really does not have an effect in terms of how welds fail when they're dynamically loaded. Now, one thing you'll also notice that's really interesting about this graph is that normally when we have fatigue, when we look at fatigue versus, or number of cycles versus the stress, we're actually looking at the alternating stress over here. But since all we care about is the stress range, then that's what we're going to be plotting against for these SN curves for welds. One final thing to note about these SN curves and how dynamic loading works in welds is that we don't actually need to worry about correction factors for finding the fatigue strength in welds. And this is because the test data that was collected, so all of the fatigue strengths that are found for materials have all been found via experimental methods. And so normally when we test a unwelded material, we have a very nice polished little dog bone sample that gets tensile tested or torsion tested or whatever method of testing that they're doing. And when we do that, it's a very perfect little specimen. It's polished, it's got a very high machining tolerance, But that's not necessarily the case for these welded. And actually, the tests that have been run on welded materials are actually close enough to the actual material that we weld with that we don't need to worry about correction factors when looking at especially for surface finish, size, and that sort of thing. The testing results were close enough to what is nominally welded in machine shops around the world that we don't have to worry about adding these knockoffs to our fatigue strength. So one of the main things that does actually influence, rather than these knockoff factors, is the configuration of the weld. And so a group called AISC, which is the American Institute for Steel Construction, tested a bunch of these different geometries and made a really big table that you kind of see a section of here with different categories of welding geometries. Now, these different categories there's tons of them. This is just a really small sample that's in the book. And you can go look up all these different geometries that are available. But they came up with 8 different ones: A, B, B prime, C, D, E, E prime, and finally F. Now, starting with A and going through E prime, starting with A has the highest resistance to fatigue, and E prime has the lowest resistance to fatigue. Now, what you'll notice with category A, which is up here, it's just the base metal. There's no welds. It is just the wrought material that you would normally see tested. And so all these different categories, what they've gone through and done is figured out how that weld introduces stress concentrations into this geometry. And so what that does is it allows us to figure out some really nice equations to look at the allowable stress concentrate, or the allowable strength for different weld types. So category F is different in that it is the pure weld material. So like category A, we have just the pure base metal. Category F is the exact opposite in that it is just the base, it is just the weld metal. And so one of the interesting things too, that when we look at the SN curves for welds, is that we don't use just the average of the fatigue strength values that were tested. What they actually did was use two standard deviations off of the average to build a window of these values. And what that does is allows us to have less of a reliability knockoff when we're calculating the fatigue strength of these materials. And so two standard deviations is 95% confidence. So what you'll see over in this table is that for percent reliability, your 95% reliability is equal to a coefficient of 1. So for all categories except for category F, which is just the pure base metal, to find the fatigue strength value for these different configurations, we use the equation that the fatigue strength is equal to that reliability constant times CF over N, which is the number of cycles, raised to the 1/3, and that must be greater than or equal to the endurance strength due to the stress range. Now, both this CF and the SER come from this table, which is defined for different materials. These are for particularly hot rolled steels, and so that it gives a different category, and then also shows what the value of those coefficients are for that material. Now, category F is just only slightly different in that the fatigue strength is equal to C reliability and times the CF over the number of cycles, but is raised to the 1/6 instead of to the 1/3. And that also needs to be greater than or equal to SER. Now, CF and SER come from that same table. You can see that it has a row for F right down there. And so It makes it really easy when we want to use this value to calculate the factor of safety. All we need to do is just plug it into the following equation for welds. And so this is going to be SFR over the applied stress range. So like I said, for dynamic welding, or for dynamically loaded welds, it is all dependent on that stress range, which makes this so nice and simple. So one of the other things we can do to make this even easier on us is to look at the concept of using a line to describe a weld. So what we're doing in this case is defining the throat area as a single unit of length. And then, so these different geometries have certain load on them. And so what we can do is create a load per unit length and then correlate that to the actual, correlate that with the amount of stress and the amount of force. And we'll go through an example with this to make sure it's real nice and clear. But again, one of the nice things about all this stuff being so heavily governed by different bodies is that there are a bunch of tables that describe for different geometries how we find these force per unit lengths for these different welding configurations. So there are a couple base equations that how we take different loading conditions and turn them into these force per unit areas. So for direct tension or compression, it is just that force per unit length is equal to the load over the area. Well, and it's not exactly the area. You can see that for each of these different configurations, we have this AW, SW, and JW, as well as definitions for moment, torsion, and also a dimension for how to find the arm of torsion. So for direct shear, it's very similar. That force per unit length is equal to the shear load over AW. For bending, it's FB equals that moment over SW, which we again get purely from this section of the table. And then for torsion, it is FT is equal to TC over JW. So, between these four equations, we can take any sort of loading condition that we normally see and turn that into a force per unit area, so that we can more easily analyze these different welds. And we're going to show you how to do this in an example. If you want to follow along, this is example 16.4, which is in your book. And so if you want to follow along, that's where it is. So we're going to be taking a look at this welding assembly. It is two filleted joints that connect a wall, a pipe, and then an arm. So like it says, this welding assembly has fillet welds. We need to determine what the weld sizes are so that we can hold up a dynamic load that oscillates between -80 and 600 pounds for infinite life, and we want to make sure that this assembly has a factor of safety for fatigue of 1.5. So we're going to say that this is ASTM structural steel and that we're using that E70XX welding wire, which you'll remember from previous, that the 70 here means that the ultimate tensile strength of that wire is 70 kpsi. So we're going to use Schedule 80 pipe at 4.5 inches of diameter for that pipe, and the wall thickness is 0.337 inches. So, and then we've got a couple dimensions of the assembly, of the length of the arm from the edge of the plate to the other edge of the arm, which is 15 inches, and that the arm has two center distances of 10 inches. And so you'll notice that the only load applied here is out here at P, which is attached to the arm. And so we're being given that this is a category C weld. Now that goes back to that table by AISC, so you'd have to go to that table and figure out what exactly makes this a category C, and that's something that's being given to us in this case. So we're going to have a couple different types of loading that is occurring on these welds, and the first weld that we're going to take a look at initially is this weld right here, because it experiences the most of all of the different types of loading conditions seen in this problem. So first thing we need to do is determine the stress range, or in this case it's actually the force range, since as we've talked about today that all of the dynamic welding is purely driven by that stress range. So our range of force, delta F, is equal to that F max minus F min, which is just equal to 680 pounds. So like we said, this is a category C, but since this involves weld metal, what we need to do is also check for category F. So we're going to start by looking at treating this as checking to see if we are limited purely in the weld metal, and then we'll check the actual joint to determine which is going to limit us most, the joint or the actual weld metal. So the first thing we need to do is what kind of loading do we have? So we've got three different loads in here. We've got a shear of just that whole weight pulling down on the weld. We've got bending due to there being a load out on the end of this, pulling it down, as you can see down here. And then finally, we also have torsion, since this load is applied off of the center of that main pipe. So that means we've got 3 force per unit lengths to find, since we're going to treat this initial fillet weld as a line to make it easier. So we need to find FS, we need to find FB, and we need to find FT. So if we look back at the equations from previous, for this type of joint, let's see, there we go. This is a category 9 in terms of the chart of the geometry for looking at lines as a weld. And if you need to see that, that is in the book. That is figure 1616. Which is on page 980 or one of your book. That's a good one to bookmark for all this welding stuff. So we look at that. We've got this AW, we've got an SW, and we've got a JW. So we can find all of these different force per unit lengths. So for FS, it's going to be that delta F over AW, which is just going to be equal to delta F over pi d, which if you plug the numbers in, that gives us an FS of 48.1 pounds per inch. So for bending, it is a little bit different because we need the moment over SW. But if we look back at that table, that first line, it actually defines that moment is equal to P over A. And for this geometry, SW is pi times d squared over 4. And this P is just delta F. So if we plug in numbers for that, and A here, it actually turns out is the A. You can see it defined down here. A is the length of that pipe. So that's just going to be the 15 inches and is also called A in our diagram. So if we plug in the numbers, our FB is equal to 641.3 pounds per inch. And finally for torsion, we've got this TC over JW. And so T is defined as the delta F times A, which is the length which is the distance off of center from the distance off of center from where the force is applied to the center of the pipe. And then C is actually the diameter over 2. So, and then JW you can see down here is pi d to the third over 4. And when we plug in the numbers, that becomes 213.8 pounds per inch. So what we're going to do is we need to find out the total amount of force that this weld is experiencing. And just a reminder, we are looking at this weld right here against the wall. So we're going to find the total magnitude of force, which we're going to call, we're going to call that FR, and it's a square root of the sum of the squares of these different forces per unit length. So Fs squared plus Fb squared plus Ft squared. And when you plug that all in, you get that the total force is equal to 678 pounds per inch. So that's great. We now know the total amount of force that is due to the fluctuating stress that is being felt on this certain weld. So the next thing we need to do is look at our table for these different categories of geometry. So like I said, the problem says that this is category C, but we need to check and make sure that the weld metal is not going to be the limiting factor. One thing you can see is that for category F, we've got the lowest KPSI, so it kind of makes sense that we're going to check this because the weld metal, as we discussed before, you want to undermatch that to your base material so that it actually is a little bit weaker, so that any failure is going to occur in that weld. So we're going to use that as our endurance strength due to the stress range. And so what we're going to do is find, using that equation we discussed earlier, where the factor of safety is equal to the SFR over delta sigma, we want to figure out what our maximum allowable stress range is. So if we end up solving for that and using SER as our maximum, which it is since we're not using a certain reliability, and that's what the absolute maximum endurance strength would be, we can figure out that our allowable stress in this weld is equal to SER over the factor of safety. And from the problem, we know that FOS is equal to 1.5, and SER from the table is 8,000 PSI. And so from that, we know that our allowable stress that we can have inside of this weld is 5,333 PSI. So really easy to get an allowable stress from the factor of safety, purely based on the geometry that we are welding with. So this is where the beauty of treating these welds as a line really comes in. So we know that our allowable stress is equal to 5,333 PSI, and we know that the amount of force that we're seeing is FR, and that's equal to 678 pounds per inch. Now do remember that PSI is pounds per square inch, so this is really 5,333 pounds per inches squared. And so this is where we can actually relate these two values to each other to get a to find the throat length of the weld. And if you'll remember back from the initial stuff when we were talking about the geometry of welds themselves, the driving dimension on welds is the throat length, which, if you remember back, if we're looking at a complete penetration groove joint, the throat dimension is here. Is that basically the thickness of the plates. And if we're looking at a fillet weld, so between two things here, here's our weld, your throat is this dimension right here. So this is what we're looking for. So this is where the beauty comes in that we can just take that the throat is equal to the force per unit length over the allowable stress. And if we look at the dimensions for these, or the units for these, this is pounds per inch over pounds per inch squared, which is going to result in an inch measurement, which is exactly what we want because this is just a single length measurement. And if we plug the numbers in for this, we figure out that the throat that we want for this fillet weld right here against the wall is equal to 0.127 inches. Now, for fillet welds, we don't necessarily talk about them in terms of the throat necessarily. We really actually care about what are these legs. This is W, the leg length of the joint. And since this is going to be a 90-degree weld, or 90-degree joint, we know that this angle here is 45 degrees. And so we can just take that throat and find W is equal to 1.414 times the throat, which that just comes from geometry of the triangle. And so we get a leg width of 0.180 inches. Now, what we want to do is round up to the nearest. Usually these are measured. You got to think this is not necessarily done by a machine all the time. This is done by a human welder. So we want to round it to a nice measurement that they can actually measure with their tools. And so we'll round this up to the nearest 16th of an inch, which is 3/16 of an inch. And that is equal to 0.187 inches. So just 7/1000ths of an inch bigger. So really doesn't impact what we're looking at here so much. But the good thing to note is that this is the length of the leg of the weld that we need to put down to achieve a factor of safety of 1.5. And if we actually look back at the table that we talked about a couple weeks ago that describes the minimum thicknesses for welds for different thickness and base materials, if we look back at that table, one of the categories is for the thickness between a 1/4 inch and 1/2 inch. And we said that the thickness of this pipe was 0.337 inches. So that falls within that range. And for that, the minimum leg length for a fillet weld is 3/16 of an inch. So that perfectly falls within what we need, what is designed by the governing bodies of AWS and AISC, that they've said is the proper size of weld for this type of situation. So finally, the last thing we need to do is check that our assumption that the weld metal is going to be the limiting factor is actually the case. So what we need to do is actually determine the von Mises stress occurring in this weld so that we can determine whether or not, or actually, we actually don't need to worry about this weld as long as we put down the same weld that we have put down here. Since if we put a 3/16 inch weld here, there's no bending occurring at the secondary weld over here. So since that's the case, there's less force per unit area on this weld. So putting a 3/16 inch weld will actually have a higher factor of safety than the weld against the wall. So looking at this weld against the wall again, we need to determine if we look back at our fillet weld, which looks something like this, we want to determine if this section right here where the wall and the fillet weld meet, if that is going to rupture. So we're going to use category C, and we're going to treat this as a little bit more of a standard stress problem by finding the von Mises stress. So we're going to look at the two different stress states that are going to produce the stresses. We've got the stress due to bending that we have found before, where sigma x is equal to mc over I. And from that earlier table, we know that m is equal to that delta F times C, delta F times A, which is the length of that pipe, times C, which is half the diameter of the pipe over I. And if you plug all those numbers in, that's going to give us a normal stress of 2,388 psi. Then we also need to find the stress due to that torsion loading, and that's just tau xy is equal to TR over J, and that TR is equal to the delta F times the distance R here that is shown, and that is also times the C, which is the diameter over 2, since we want to see what's happening up on this top surface, and that's divided by J. And so if we plug in all those numbers, then we get that tau xy is equal to 796 psi. So from that, we can find principal stresses. We've done that all semester. And so plugging those in, you get sigma 1 is equal to 2,629 psi, sigma 2 is equal to 0, and sigma 3 is equal to negative 241 psi. Now, we've got the von Mises equation. Sigma prime is equal to square root of sigma 1 squared plus sigma, square root of sigma 1 squared plus sigma 2 squared plus sigma 3 squared plus the interactions of sigma 1, sigma 2, sigma 1, sigma 3, and sigma 2 and sigma 3. But since sigma 2 is equal to 0, we can simplify this pretty good and get it all the way down to that sigma prime is equal to the square root of sigma 1 squared plus sigma 3 squared plus the interaction between sigma 1 and sigma 3. And so if we plug in our principal stresses that we found, that gives us a von Mises stress 2,757 psi. So for category C, if we look back at the table for infinite life, the fatigue stress, or the fatigue strength, is equal to 10,000 psi, and that's dictated by AISC again, and you can find that in the table that lists all those out. So to find the factor of safety, all we have to do is plug in SF over sigma prime, and plugging those two in, we get that the factor of safety at this part where the weld metal meets the base metal on the leg of the fillet joint is equal to 3.62, which this is quite a bit greater than that 1.5 that we see in the weld metal itself. So all that tells us is that the weld metal is going to be actually the limiting factor for this joint. So with all that, that's the end of the content for today. If you have any questions, feel free to shoot me an email, and we can talk about it further, either over a Zoom or just over email. And thanks for listening.